Couple here, and maybe one or two I see in the middle.
Oh, no,
Okay, I guess we will slowly begin and let people trickle in. Welcome, everyone, to the Simons Institute. I am Sampath Kannan. I'm the Associate Director here. For some of you, this may be the first time at the Simons Institute, so a brief introduction about the Institute. Founded by a generous grant in 2012 from the Simons Foundation, this institute brings together the leading researchers in theoretical computer science to examine the nature of computation itself. But we also look through a rigorous algorithmic lens at other disciplines and technologies. In particular, we'd like to make sure that we understand the technology ideally before it's deployed. And since information technology has so much of an impact on today's society, we want to engage with a very broad audience when we talk about technology and what it means. And this event, a panel, which is part of the Theoretically Speaking series here, is very much in that spirit. So it is about engaging not just scientists, but also the public in the surrounding areas on technologies. And my task is just to introduce our moderator, Anil, who will go on to introduce the panelists, the distinguished panelists. Again, our moderator is Anil Ananthaswamy, who is a science communicator in residence here. Anil is an award-winning journalist. He was a deputy news editor for this New Scientist magazine. He has been an MIT Knight Science Journalism Fellow. He contributes regularly to Quanta, Nature, and Scientific American, among other magazines. He's the author of 4 popular science books, the first of which, The Edge of Physics, was voted the Book of the Year in 2010 by Physics World. His latest book is Why Machines Learn, very relevant to today's panel, The Elegant Math Behind Modern AI. It was named one of the 5 best AI books of 2024 by The Information. Welcome, Anil. Take it away.
Thank you very much, Sampath, for that introduction, and welcome, everyone. Can you hear me? Yeah. Sampath, can we get that? Yeah, we'll give it to... We'll just give it to them. Yeah. So, welcome everyone to this Theoretically Speaking event on the past and future of large language models. It's my pleasure to introduce our distinguished panelists. We have, to my right, immediate right, Azelia Mir Hosseini. Azelia is Assistant Professor of Computer Science and founder of the Scaling Intelligence Lab at Stanford. Her lab develops scalable and self-improving AI systems and methodologies towards the goal of advancing artificial general intelligence. She's also a senior staff scientist at Google DeepMind. Prior to Stanford, she worked at Google Brain and Anthropic. Her past work includes mixture of experts, neural architectures, automating and optimizing computer systems and chip design, and research on inference time scaling laws. She received her PhD in EECS from Rice University. So welcome, Azelia. And to her right is Luke Zettelmeier. Luke is a professor in the Paul G. Allen School of Computer Science and Engineering at the University of Washington, which is also my alma mater, so yay. And a research director at Meta. Luke's research focuses on empirical methods for natural language semantics, designing machine learning algorithms, introducing new tasks and data sets, and most recently on how to best train and deploy large language models such as ChatGPT. He is a fellow of the Association for Computational Linguistics. He won the Presidential Early Career Award for Scientists and Engineers from President Obama, an Allen Distinguished Investigator Award from Paul Allen, and multiple paper awards at the top NLP and ML conferences. Luke received his PhD from MIT. So welcome, Luke. And to Luke's right is Dilip George. Dilip is an engineer and scientist working on AI, neuroscience, and robotics, and is currently at Google DeepMind. Dilip co-founded 2 companies, Vicarious AI and Numenta. Vicarious was recently acquired by Alphabet, and Dilip and his research team joined DeepMind to accelerate progress towards AGI. So we'll get to hear about that. His research focuses on understanding brain mechanisms, in particular developing a detailed theoretical model for thalamic and cortical microcircuits and place cells as sequence learners. He did his PhD at Stanford University. It was during his PhD that Dilip co-founded Numenta and co-developed the ideas behind hierarchical temporal memory. So welcome, Dilip. And again, welcome everyone. The topic for today's panel discussion is the move towards AGI, why large language models surprised almost everyone, and what's coming next. So this audience is a mixture of experts. So I will talk briefly about large language models and some terminology to get us all on the same page. Some of this will be very trivial for some of you, but for others may not be, so hopefully bear with us. So we would have to be hermits living in caves to not have heard of LLMs. It seems so long ago now, but it was only November 2022 that OpenAI launched ChatGPT, and AI and machine learning as we know it changed dramatically. But what is a large language model? I just want to give a brief overview before we ask the more difficult questions of the panelists. So a large language model is a deep neural network-based machine learning model that's been trained to predict the most likely next word to follow some input text. So when you type some piece of text into ChatGPT's user interface, it takes that piece of text, predicts the next word, appends that word to the initial input, feeds it back to itself, predicts the next word, and keeps doing so until it produces some end of text token, signaling the end of the text generation process. You're probably going to hear the word token used a lot in the discussion. It simply refers to how text is broken down before being processed. A token might be an entire word, or part of a word, or even a single character. The details don't matter for us today. We can think of words and tokens interchangeably. In ChatGPT, GPT stands for Generative Pre-trained Transformer. The transformer refers to a deep neural network architecture that was first detailed in a paper in 2017 from a research team at Google. The pre-trained part refers to a model that has been trained on large volumes of text. Generative refers to a model that creates or generates new data that statistically resembles the data on which the model was trained. So leaving aside the engineering challenges, the training process is conceptually rather simple. You take a piece of text, mask the last word, and ask the model to predict the blanked out word based on the information that's contained in the rest of the sentence. Initially, the model will get it wrong. You can quantify the error that it makes and use that to tweak the parameters of the model a little, so that if you gave it the same sentence with the same blanked out word, it'll do a little better the next time. You keep doing this until the model gets it right. Now think about doing this for every piece of text you can find on the internet, copyright issues notwithstanding. Once a model can correctly predict the next word for almost any piece of text, then you can confidently say that it's modeling the statistics of written language. So as we'll hear from our panel, models like these were in the works before November 2022, before the world awoke to this phenomenon. And those in the know were aware of what was coming. And yet, just making these models bigger by using more parameters, more compute, more training data, unleashed something quite powerful and caught many off guard. Of course, since November 2022, the models have become much, much bigger, and new techniques have extracted more sophisticated, quote-unquote, reasoning behavior from LLMs. With that, let's talk to our panelists and see what they think about where all this is going. But first, let's just look back into the past 2 years, and maybe I can start by asking, what surprised you most about LLMs when they hit the big stage? Luke, let's start with you. You come from an NLP background, so you were doing some of the kinds of things that LLMs have eventually started doing. How aware were you of what was going on prior to 2022, and did GPT-3 surprise you?
Oh, yeah. So thanks for inviting me to the panel, and that's a great question. I was very surprised. It's kind of hard to really describe all the ways that it changed things. You know, GPT-1 had been out for a while. We had done some work on Elmo and other things, so we sort of knew a little bit that scaling would make things better, like training on more data obviously is going to make things better. But sort of the size of how big they were able to go, how fast, and just how much that changed the behavior of what the model would do was just unbelievably shocking. Everybody knew they were scaling it. We knew it was coming, but we had no idea like how much better it would be. And just one example of that that I've sort of resonate a lot with is kind of pre-GPT-3. language generation, like having an algorithm write a whole document, was considered sort of almost unsolvable. And in particular, even getting it to be grammatically correct. So no grammar errors, like no mismatched, no wrong determiners, no other things, was considered a very, very difficult problem. And then overnight, it was just completely solved, like superhuman level. Like I know a lot of non-native speakers in this room probably use these tools to improve their writing, and probably native speakers too, and they're just superhuman. They're so good at it. And it was considered sort of almost impossible from an NLP perspective, even a year or two before that had happened. And there's many, many other aspects. We'll talk about reasoning. We'll talk about a lot of other stuff tonight. But even like simple grammar and fluency, was just a huge phase shift. And that shows you kind of how fundamental it was, at least from my perspective.
And Azalea, what surprised you about when GPT-3 came on stage?
Well, I wasn't surprised. At the time I was at Anthropic, we had access to models that were probably just as good. So the surprising moment was like the adoption and like this really amazing kind of like popularity in terms of general public model. So that was the most surprising part.
But in terms of the capabilities, I remember when we had a chat earlier, you talked about how the ability of these models to do one-shot or zero-shot learning. So could you just explain what that means and why that was such a big deal? Oh.
Okay. Yeah. So maybe the most interesting or one of the most surprising moment came before ChatGPT, and that was in 2020 when this paper came out and kind of characterized scaling laws for pre-training. So that was a very interesting observation that, again, we can characterize how these models keep becoming better. And not only they become better, but also there's this power law, and we can kind of predict how much they're becoming better. So that was like a very important moment to say, okay, now we have a recipe for success. And at the same time, around the same time, this with GPT-3 and other kind of work around it, the few-shot kind of learning ability of the models to just learn from a few examples and really be able to solve similar, maybe slightly out of distribution problems with just a few examples. This was a very, very interesting kind of observation that basically made these models much more interesting and a lot of more attention.
So by zero shot, we simply mean that we just ask the model the question. Potentially, it hasn't been trained on that particular task, and yet it's able to solve that problem. And one shot would be just you provide.
You give an example of the model. Like the more general example would be like the model. You want the model to translate from English to French, and then instead of asking, here is a new word or here is a new sentence, translate it for me, instead you just show a few examples of how here is a few sentences in English, and here is their translation, here are their translations, and now here is a new sentence. So these were the early examples of how few-shot learning was working, or
And the amazing thing about this is that it wasn't specifically trained to do any of these things. It was just trained to do next token prediction and this. So I'll come to you, Luke. I know you have something to say, but I want to get Dilip's view. Dilip, you come from a background of robotics and embodied learning. So were you impressed by LLMs when they broke through?
Impressed, definitely. So just to give a little bit of perspective, I never believed in NLP as a thing, in the sense that I never believed in, you need to have grammar and all the other entity recognition, whatever there was. I never believed in such a thing because, I didn't have that background, and I never believed those as real things, in the sense that I always believed that a good sequence model would be able to do language tasks. That I believed. It's probably from the old Shannon days. Right? Shannon had that example of sequence generation in his information theory book, and since I did not believe in this grammar idea at all, that I believed that is a fundamental principle, but still GPT-3, GPT-4, all of them were surprising, especially how it is doing in context, how it is able to do in context learning, because that's not something that you typically think about as a pure sequence prediction thing, right? It's something different, and this slot mechanism where it can just pick up something and insert it into a slot from the past, and those kinds of behaviors and circuits emerging, that was super surprising to me.
And just again for our audience, when you say in context learning, is that the same as one shot?
Yeah. So that paper where they showed that language models are zero shot learners. So that was extremely surprising, that behavior, where you can give an example of something in the prompt and it will pick up on what is the rule being shown in that example and apply that rule to a completely different set of symbols that was not seen in training. And that was extremely surprising, and of course many other things like instruction following, everything which we're specifically trained for, those were all surprising capabilities.
Yeah. Luke, you were about to say something controversial.
I don't know if I'm going to be controversial, but I'll try to pick fights for fun. So I actually found zero-shot learning completely unsurprising. In context is kind of interesting, but zero shot, so the idea that you could ask it to translate something and it would do it. But remember, these models were trained on the whole internet. So, they've seen web pages teaching you how to do translation, and they've read them. And they've seen example sentence pairs. And not only have they seen it, but even if it's a tiny, tiny fraction of a trillion, which is how many words it's trained on, is millions of examples. So what's fascinating is that it could actually pull out this stuff that's even kind of a small percentage, but a big in an absolute sense. But in some sense, there's no even notion of a zero shot means you've never seen it before. But when you've trained on the internet, it's really hard to find something you've never seen before. It's all in there. But it's cool that it gets it out. That's kind of surprising. But the fact that it can do it at all, if you think about the data and you think about what it was trained on, it's seen it before. It's seen it all before.
That's not controversial.
I think it's still interesting that it can mix and match. For the translation, it can.
Celia, if you can keep the mic closer.
It might have never seen translate this sentence to French, right? It can mix and match kind of its learnings, and it's also interesting that it has seen so much data and still able to extract a lot of this information.
And like you were saying, the 2020 paper about scaling laws, that really set something in motion. And I think in your talk you also referred to how this has become kind of the recipe for companies also to justify what they're doing. So can you speak about the impact of those set of laws, the scaling laws, and also a little bit about what the laws are telling us?
So basically this scaling laws, the traditional one, which applies to pre-training, says that as we pour in more data or more training compute or increase the model sizes, the model does better. Specifically in this case on test loss and the loss, but also which correlates with the capabilities of the model. But not only that, we can quantify how much it becomes better and predict its future behavior for additional compute. So before training a bigger model or before throwing in more data to this model, we can predict, given this curve fitting that we've done, we can predict where the model is going. So and then that's kind of a recipe for training the next generation of bigger models, because for a certain kind of performance or capability, we would know how much additional resources we need. And this is granted that we are not changing a lot of these recipes or other optimizations that will come along the way, but
so at the high level, that's the. So Luke, do you think there's more headroom here with these initial set of scaling laws?
I think we should try to push everything to the extreme, even though it's becoming billion-dollar experiments at this point. So it's quite challenging to do that. If you look at the shape of these curves, though, they're power laws. And what that roughly means is you need to 10x the amount of data and compute for a constant gain in performance. So just based on the shape of the curves, you can already predict that the scaling won't work forever. There will be a limit of how far you do it. It's not like a linear growth, right? You actually really, it's a log scale. You really need to keep doubling stuff to get the performance gains. And so I think it's a really interesting research question. Can we invent scaling recipes that have different shapes of curves? It probably will never get linear, but it's something that looks better. And I think it's also an interesting question to see how far can we push what we're doing, but we're going to run out of data. There's only so many GPUs in the world. I mean, there's a lot, but at some point we're going to run out. And I think for text-only models, we're getting pretty close, honestly.
Right. And Dilip, you have kind of in your public writing sounded some alarms over this unbridled scaling and the focus on that. Could you talk about that?
Oh, I'm not alarmed. It's great. I'm with Luke in the sense that we should explore it to the maximum, right? At the same time, all asymptotically optimal algorithms have scaling laws, right? It's not a property of just LLMs. You can take Lempelsive algorithm and draw a scaling curve. It's just that it will be much more expensive for getting the utility out of it, right? So all algorithms which are asymptotically optimal can scale, but nobody's going to spend the money to scale it. Here we can get utility out of it while scaling it. That's why we keep scaling it, right? And at some point, we will hit the diminishing returns. It's not because the transformers won't scale beyond that. It's just that you won't be able to justify the cost. But I don't think we have hit that yet, but we will at some point. I don't know whether this is the right point to bring up the analogy that I have.
Yes, please do. That's what I was trying to get out of you. Yes.
So I have this analogy with what happened in the aviation industry. Almost in parallel, 100 years ago. If you look at how aviation made progress and what was the dominant technology in the 1920s, it was not airplanes. It was so airplanes were invented in 1903. That was when heavier than air flight was invented. The Hindenburg accident happened in 1937. So in 1937, we were flying transatlantic in balloons. It was not airplanes that was taking people across the Atlantic. It was balloons. If you ask anybody in the 1920s, what is the scalable technology for building aviation? They will say balloons. What was the control substance? What thing did USA prohibit exporting to other countries in the 1920s? Helium. So why?
Not GPUs.
No, not so. Well, which is the helium now? So it was not. It was. And why did this happen? Because there was a scaling law, and people found it just easier to build and scale balloons. And once you hit that scaling law and a recipe, and once you can get value out of it, just resources will pump into that until you run out of runway. It's not because it runs out of runway. It's because other technologies catch up to that it goes out of fashion. So, and in fact, New York Times had this quote in 1903, and it's a favorite quote. It says, in most things, the variations permissible from plans and calculations is not fatal to utility, and in any other form of flying machine than a balloon, the least margin of variation permissible in exact mechanics is probably much too wide to warrant the expectation that the results sought will be attained. So there was just heavy skepticism about heavier than air flight, and people figured out that, look, we don't have to figure out the principles of flight. We don't have to make something that really fly. We can still go through the air and land from, go from A to B, just float through the air and go. So, and that's, in my mind, that's where we are with cognitive technologies. We don't have to really figure out the principles of how intelligence works, but you can still make machines that do intelligent things. Might be more expensive, less controllable, way bigger than in terms of compute that that the brain might be using, way less data efficient, but this technology will run its course, and it's you can't stop it right now because we still have lots of juice to extract from it, and it's extremely useful, and My bet is that there is room for finding out the real principles that power intelligence, and a new set of techniques will emerge. It's just hard to predict when. Heavier than air flight caught up only in the 1940s. It took 30 years of technology development.
So maybe something is coming. Actually, that's a good segue to Azalea. In your talk again this morning, you mentioned that there's a new set of scaling laws that we are kind of beginning to embrace. Right? So what we just talked about are the laws that apply to LLMs when we train them, and now it's shifted to sort of scaling laws that apply for inference time or test time. Can you explain that a little bit and tell us why this is a big shift in what's happening?
Yeah, so basically scaling laws during inference is this phenomenon when we can get a whole lot more capability out of a pre-trained model without...
It's on, yeah.
Is it on? Okay. We can get a whole lot more capability out of a model without doing any kind of a fine-tuning or additional training, but just with basically applying this compute during inference, which could come in different ways. It could be asking the same prompt or the same question over and over again, or serially ask the model to revise its own outputs, interact with the environments, and use tools to update and modify the generations. Is there a question?
Maybe after we finish, yeah? We'll hold on to your thoughts. I'll come to you first. Okay. Yeah.
So the reason this is very interesting is just it opens up a whole new frontier for translating additional compute to new capabilities. And it's much cheaper than pre-training, right? We can spend $100 on like a Llama 8B model and make it go from 10% on this math data set to 70%, assuming that we have a verifier, or for coding tasks and all that. So it's like a cheaper kind of frontier for kind of bringing capability to the models, and it opens up a whole lot of new opportunities.
And so you believe that there's, again, much more headroom that has opened up for scaling, for throwing compute at the problem.
Exactly. I think in my talk today, I kind of touched on how the models are, this scaling inference compute can make the model a whole lot better at the generation task. And then, so that frontier keeps getting better and better, generating meaning, creating candidates that could possibly solve a problem. And if we can kind of apply or bring that to the verification or selection piece, then this is very powerful. And in a lot of cases, in many domains, we have these verifiers built in, or we have access to automated verifiers. So this kind of
by verifiers, we mean automated systems that can check somehow the output of the LLM.
Because algorithms are better at generation than at verifying which one of their generations is correct, or when they should stop and generating final answer.
So I do want to come to Dilip's kind of analogy, metaphor about the next, what might constitute heavier than flight in the context of intelligence. But before that, Luke, with these new trends in scaling laws, when we move to inference time scaling, what are your thoughts about what's happening?
I think it's a really cool advance, and I think we're seeing a lot of really interesting work very recently on it. It's not clear. So two big challenges. If you're not in a domain like code or math where you can easily verify the correctness of your final output, then we kind of don't really know how to do it yet. So I'd love to see more work that's a lot more general. There's a lot more to AGI than the sort of coding and math problems, which are a great place to start. But we have a lot of work left to do. And then it's not clear, just like we were talking about before, how do you get to the end of the curve? My prediction is that inference scaling, we're going to get to the end of the curve a lot quicker, but it's still a good thing, and it will always be kind of like a crucial part of the toolkit. It's very interesting to study.
And can I ask you also just, these language models now have kind of shifted from being called large language models to large reasoning models. Can we just talk a little bit about what one means by these reasoning models?
Yeah, so reasoning is kind of hard to define for me, and maybe other people have a good definition. But one way to think about it is like the sorts of things that we find pretty hard, like college level math or PhD level math or coding competitions, things that require multiple steps. That's, you could think of that as reasoning. Like maybe when you solve it, you can't just do it in your head. You need to actually take a pen and pencil and kind of write out the steps and really think about the problem very carefully. Those are sort of reasoning type problems. And I think one really cool thing that's happened, I don't know exactly when, but as part of the scaling of inference 2 is sort of you get the models to talk out loud. So they sort of generate a whole document, sometimes called chain of thought. They'll like write a whole document and they'll list their own reasoning steps and kind of think, okay, well, if I want to solve this word problem, the really important thing is this thing, and then I need to multiply it by that, and then I need to do this other step. And sometimes those reasoning chains are completely bizarre. Like we actually showed that you could mess with them and make them incorrect and it would still help you get the right answer. So sort of exactly what's going on is very noisy and hard to understand. But it really makes the models do much better on many different tasks. And it's a really cool phenomenon. Like the model can just kind of think in words and actually create a document and do a better job at many, many problems.
So, one of the things that has happened because of LLMs and their broad general sort of expertise on a broad range of problems has been this developing buzz about AGI or artificial general intelligence. And I bet that each one of you has a different definition for what AGI is. So, Azalea, your take first of what one means by AGI before we see how we can get there.
Yeah, so when I think of AGI, at least the first kind of phase of AGI, let's focus on like tasks in which like a human is sitting behind a computer and doing any task that can be done in software. So let's not bring the mechanical and physical parts to it. So AGI means like, to me, it's something like the AI can do better than most human at important tasks, or maybe all tasks that require a human sitting behind a computer. So the generality comes from the AI. Human experts can become experts in a few things, but the AI can become an expert in everything that a human can ever be an expert in.
Correct. And Dilip, again, from your perspective, from robotics and embodied agents?
In some sense, I agree with Azalea in the sense that, okay, if a human can do anything behind a computer, if an AI system can do that as well, then it is AGI. But what is an example of a task that cannot be put on a computer? I don't know an example of a task that cannot be put on a computer. For example, when my HVAC person came to remodel the house, okay, he had to walk around the house to infer how the ducts are going through, where the ducts are going. Quite a complex reasoning problem because things are hidden, quite an inference problem. Now, I do want, if a system cannot solve that task, it is definitely not AGI for me. Can this task be put on a computer? Yes, of course it can be put on a computer. Is anybody going to put that on a computer right now to test it for it? Nobody is going to put that on a computer because that's not an important problem in some sense because the problem occurs in the real world and not in the computer. So in one sense, I agree with Azalea that that is a reasonable definition. But I want to bring out some of the. To me, it's not the skills that it demonstrates. To me, it's its potential to learn. A 5-year-old child is AGI to me, or like let's say a 10-year-old child. Like, even if the child hasn't gone to school, is AGI to me in the sense that that person has the potential to acquire all the skills that is needed. I can expose that person to a curriculum that learn the skills, and that person can be a doctor, engineer. Now I can make 10 replicas of them. They can be all experts in many different fields. And what is the capability there? It's not the particular skill that they have acquired at that moment. It's the ability to acquire the skills in a data efficient way. And to me, that is the primary thing.
Okay, and that's certainly something LLMs don't have right now. Luke, do you have your definition for?
Yeah, my definition is not too different. So it's sort of, It's hard to define precisely, but you kind of know it when you see it, sort of situation, I think is what we're all saying. I would sort of riff a little bit on what Dilip was saying and say, I actually think we won't get there without embodiment, that you actually kind of have to live physically in the world. I can't prove that, but that's my intuition. And that it will be very controversial, because even like the models that we have now, say the text-only models, they're seemingly, very intelligent in certain things, but they also fail sort of catastrophically in weird ways that a person never would. Like slight rephrasing of things can cause it all to fall apart, or they learn in such a data inefficient way. So it's really hard for me to think about like all the different facets. It's not just capabilities; it's also robustness. It's also hallucination. It's also all these other things, and it's also common sense, which you probably have to be embodied to really get. And it's just a lot. And so kind of listing out sort of, if we had 200 benchmarks and we did well on them all, that would be AGI. That's not really enough for me.
Can I add something?
Yeah, of course.
So it's like asking what's the definition of an iPhone. You cannot define an iPhone. You can have a set of functional requirements, right? So I think we will have rough set of definitions which are all mostly inspired by human brains' work. We are all benchmarking against that, in the sense that how do we know we don't have AGI right now? Right, but that's because we have something that is AGI, and we can compare against that and say, look, it's making mistakes and that is the definition that will pull us through. How do we know we don't have it right now? Right, and that delta is what just takes us to that. That's it in my mind. Yeah.
So given the definitions, I can see that for Dilip and Luke, LLMs are not going to get us there. But from your definition, Azelia, scaling LLMs alone could get us to something very close to the kind of AGI you are thinking about.
I think, first of all, when I say an AI that's better than most human and like all tasks, I think it kind of like that to some extent it comes with it. It should be robust, it should be reliable, because that's where most humans, like the
necessary
expert
condition
humans are in those tasks. But in terms of scaling, of course, scaling, like we show the scaling laws for training, for inference. It always it's always easier said than done. Like whenever we go to the next 2x or 10x in data size, in model size, there are a lot of problems or new challenges that come, whether they're engineering challenges, numerical challenges, everything that comes with it that needs to be solved. But somehow in the past few years, there are a lot of smart people working in this field, and those problems are kind of solved. Like we are not stalled by any means. So I think I'm very hopeful. Maybe a few months from now or next year, we find a new kind of source for scaling, or kind of this data flywheel. We make that work, and we get to a new frontier on that. But I think this flow is moving real quick, and there's no sign of slowing down. In fact, things are improving much faster. And in terms of embodiment, I mean, it's good. Of course, if we have more modality, we learn more from. But even if you think about people with disability, people who can't see or they can be really, really intelligent with just much more limited kind of modalities or senses. So I think that's why I'm very hopeful about the models we have and the rate of progress at which we are seeing. And if we have a scaling loss or kind of a prediction for the innovations that people do along the way, and it kind of seems to be going very well. So I'm very hopeful that the current flow gets us there, but new innovations make it happen faster.
Faster, easier.
Yeah.
Talking about new innovations, Luke or Dilip, given your notions of where we are headed in terms of AGI, are LLMs sufficient? And if not, what kinds of things would you want to see happen?
So by LLMs, I think you also mean all the visual language models, the whole combination, or just language alone?
No, let's take. I was going to come to multimodal models, but imagine getting.
Just language alone, I don't think is going to be sufficient for achieving AGI. That's. I think that's reasonably straightforward to understand, in the sense that. Because language is a compressed representation of the reality out there, and that compressed representation might not have all the information that you need because language is under the assumption that you can think of it as when you're communicating in language, you are already assuming that the other person has a world model inside their head, and you are communicating in the tokens that drive that world model. So it is at that fidelity, and if and so the language alone doesn't have all the information to model the world. You can put that information in, but then that will be like saying that, oh, I am going to tag every XY pixel as, that look something, and that is a language. But that's just kind of semantics at that point. It's not a language model. Like, it's an image model at that point, right? So pure language doesn't have the information, and I am certain that that is not going to lead to AGI. That I'm willing to put my money on. Multimodal models is very different thing, right? So
we'll take bets later.
So in LLMs alone, I don't know what is I don't see, you can just innovate out of the way of just pure LLMs getting to AGI. I don't see that.
I don't think it's multimodal.
Yeah, so I was going to come to that with Luke, because he's working on multimodal models.
I can combine
So maybe you can address that.
So I want to just quickly say, even people with disabilities have very rich experiences of the world.
Yes.
So I don't think that's a great analogy. But coming to multimodal, I think, for me, I still would vote on like a proper embodiment, like robotics or something. But that would be where I would feel more comfortable, and where there's going to be a lot of breakthroughs coming soon. Like, a lot of really smart people are working on that, and you're going to see some cool scaling trends. But an interesting question would be like, so if you train not only on all the text on the web, but like all of YouTube, there's a lot of information in there. There's a lot of embodied experience, even though it's only video. There's no touch, there's no taste, there's no, kicking the sports ball, there's no, action. But you can see all that happening. Like, maybe that would get us really close. I don't know. And there's a lot of work on sort of video generation models, and we saw the Sora demos and the ones that have come after, and the physics is all kind of wrong, and so clearly we still have a long way to go. But that's a place where I would bet on scale having some pretty big impact. Like, if you scale those models up, the physics will get better. They probably won't get fully solved. It'll still be weird and brittle, just like in the text case, but maybe, and then people are figuring it out. So that's where I'm not so sure.
Dilip, you wanted to finish your thoughts before?
I can add to that. I do see some things as missing in the current architectures, and I don't know whether these will get fixed by just scaling and some property emerging, or whether they will need fundamental architectural modifications, because we have been surprised by some things that emerge at scale. So I just don't know whether just make it the same architecture, just scale it up, feed it to all of YouTube, and something will emerge. We just don't know that, but we know the hints of what these capabilities need to be, and if you have played with image generation models, you can already see the problem. It's always easy to create something very interesting looking, but you want something very precisely something, it's very hard to get that. I want to have a rectangle with a dot in the top right corner. I want the left edge to be green. I want polka dots inside, and the fifth polka dot, I want a dot in it. I can make it more and more specific, right? You try to generate that, it won't get that. And whereas I can sketch this out very easily. Even though it doesn't look graphically very impressive, I can capture that idea and sketch out exactly what I want. A human can do that. So it's not a understanding in the translation of the language. It's more there is a problem in connecting that language to the actual vision. And if it happens on the generation side, if you lose precision on the generation side, the counterpart is the perception side. The perception side has the same imprecision. And this is related to things like people have talked about binding problem, where you have lots of details in the image, and if you're just compressing it using a feed-forward pass and creating an embedding vector, you don't know what all information gets captured in that embedding vector and what gets lost. something that gets lost might be something that you need to access to, and for that you have to go back into the image and access it, and this comes up across as binding problem, because the typical way it comes across as, if you have a blue rectangle and a green triangle with a red outline, etc., all this gets mushed up in the forward pass, and now it gets lose track of which object had the green outline, or which object had the green outline but with the blue corner, etc. All these details have to be kept in one embedding vector at the forward pass. Whereas,
so Dilip, I think maybe for our general audience, we don't want to get into latent spaces and but your point is that there is a lot of architectural stuff that probably needs to have changes.
I'll just add one intuition, which is basically saying in the human brain, this happens using forward pass and backward pass. We are not just feed forward machines. We access information back to the feedback pass, and we can dynamically access information, and language can drive attention back into the input, and this dynamic feedback access of information is binding. That is something that is not there in the current architectures.
So we should actually now move quickly to audience questions, but Azalea, do you want to have the last word before we move to the audience about what changes? So you've taken one perspective that scaling will get us somewhere, but do you also foresee certain kinds of changes that might be required for the next stage of evolution of AI?
Yeah, I think something that and maybe there's some similarity with what you just mentioned, is the ability for the models to learn on the go, online, as they're generating these experiences. Right now, there's some of that with bringing these experiences back in context, but context is limited. When we move on from that context, there's no natural method. We can do offline fine-tuning, but naturally we're not learning, whereas as humans we learn on the go as we have these new experiences, or generate or solve new tasks. So that would be an interesting kind of research directions for the models that we have.
Maybe we take a quick poll about how far we are from AGI, for your definitions of it. So, Azalea, how far are we? 5 years, 2 years, 1 year?
I don't know. This is a very hard question. I would say 3 to 5 years.
Okay.
Yeah.
Luke?
I think 20 plus years.
Oh, all right. And Dilip?
I don't want to make a bet. On the timing.
You were the one who put the money on the table.
I said LLMs not getting there.
Okay,
I can
right,
put the money on, but
Okay.
I can make another bet. I think the binding problem that you described can be solved with transformers and synthetic data, and will happen in the next few years.
Oh, okay.
Okay. I'll hold you.
Yeah, GPT-3 has already made huge progress.
We'll open up to questions from the audience, and Lenore has the first dib at questions.
Should we run a microphone?
Please wait for the microphone.
Yeah, so
record your question.
So please raise your hands. We'll have to get the microphone to you so that it gets recorded.
People hearing a lot of questions. Can you hear me?
Yeah.
Okay, so I have two major questions. The first one goes to your very original question to everybody. What was your big surprise? And what I want to ask is, there are 4 areas there. There is the algorithms, there's the data, there's the architecture, and I guess there was one other I was thinking of. So what are the areas that you thought were really critical to make this big jump? Is it the algorithms, the architecture, the data, actually, and the speed of computation? So those would be 4 things. Which of those were more important, or any of those, or one aspect?
Well,
That's my first question.
Yeah. I think, there's hardware gets you only so much. It's important, every generation becomes 2x, maybe some more faster. But I think the data and the model size kind of go hand in hand. In order for you to change, there's a ratio, or that ratio changes from over time, but there's somewhat a ratio between how much data you want to have for a certain model size, given our algorithms that we have. So it doesn't make a whole lot of sense to go above or below that data threshold for a given model size. So if you double the model size, then you should maybe double or do the corresponding kind of multiplier on your data for these scaling laws to work well.
So data. So then the other part has to do with Dilip. What talked about is the model of the world, and how much I see that that's kind of critical for the future, is having a multimodal model of the world. And how much do you think these current LLMs, even with they actually are somewhat embodied in the sense that they're getting feedback from the world, they're getting feedback from robots and all that. So there's a lot of that already there, and there's already a lot of multimodal coming in as well. So what role do you think they are creating models of the world already? Because I think that's going to be critical for AGI, for consciousness and all of that.
They're creating, I think they're creating some kinds of models of the world, not all kinds of questions that we want to answer using a model of the world can be answered in that question. You know, we can sit and think and do surgeries in our head on how we'll manipulate the world and then go and do those surgeries in the world, right? You know, those kinds of being able to self-modify our own structures, that kind of things don't seem to exist there. You know, we have to go and put a probe in and extract the model out by ourselves. Okay, that's so it's not clear. The model inside it is something it can manipulate and see the change. Ideally, an AGI would have such characteristics, I think, and maybe that will be an emergent phenomenon as metacognition. You know, somebody mentioned this. This was mentioned in the workshop here today. And the embodiment has to be way richer than the human feedback on, did this sentence look correct? Or it has to be more interactive, multimodal. Yeah.
Okay. Anyone else? At the very back. So.
Thanks so much for the great panel. I guess one question I had is that throughout the panel, you all talked a lot about how crucial it is to achieve some sort of embodied intelligence as a sign of like achieving kind of general intelligence. But when you think about the sort of scale of data that we have for vision and language, we don't have even like a drop. We have like a drop in an ocean of that kind of data for robotics, right? So I'm kind of curious, given this kind of data imbalance that we have between vision and language and robotics, do you guys have any thoughts on what the right path forward might be?
Okay, who wants to take that?
Thank goodness we don't have that much data, so that we can go figure out some algorithms and architecture which are right? You know, that's my thinking.
Right.
I sort of roughly agree. But I think it's a little embarrassing how much data it takes to train a language model, right? This is a great research topic. Like what the heck is it learning from the 100 billionth document that it didn't somehow learn earlier, other than some rare facts or something? And why can't we do that more efficiently? Why do we need so many GPUs to learn those final few facts? I find that really interesting question. But again, I'll say what I said earlier. Like video is probably relevant too, and there's a lot of video in the world.
Yeah.
But action is important, and video doesn't have action. Maybe you can infer it.
Yeah.
Okay.
All right.
Right. So, I think it's pretty refreshing to be reminded that there might be further better intelligence principles such that we can train models better. I guess my question there is that, do you think the current scaling law will push the language model far enough such that it can speed up AI research and development fast enough such that, for example, it can speed up research iteration for 10 times? And as a result, it's probably still much more efficient to invest in the current paradigm and then later expect the AI system to help us figure out the better general intelligence principles.
This is Azalea's wheelhouse, right? Self-improving models.
Yeah, so is the question that if we just have AI come up with new research itself? Yeah, that's definitely, I think OpenAI today released this, what is it called? Paper bench, where you kind of have the AI kind of generate the experiments for given a paper, generate the experiments for it and validate that, which is a big piece of being able to. We are seeing a bunch of papers coming out, the AI scientist paper and so on. Obviously, they're not there yet in terms of like totally new, amazing things. But at the end of the day, like, why not? I guess language models or AI can know about all the papers that have ever come out, read all the books, that have ever been written. So it's very kind of like natural for them to come up with new ideas or new kind of maybe one opportunity here is models can maybe bridge different fields together that is not very obvious to a single human expert, because human experts, again, don't have expertise in multiple fields. A lot of innovations in math domain, at least, have come from bridging different subfields of math. So it's like an opportunity here for AI to come up with new kind of science and new methodologies.
Okay.
But I think humans can still be very creative, and we don't want to fully rely on AI.
Yeah, I want to pretty strongly disagree. Sorry. I mean, I think this will happen someday in 100 years or longer. If you look at what language models are good at right now, they're good at mimicking things they've seen in their training data. They're doing almost nothing novel and creative, in my opinion. You prove me wrong. I mean, they are combining them in interesting ways. And the deep research stuff is a great framing of a problem, but it's really not working yet. It's embarrassingly bad. And so I think this is really far off. I think we should keep working at it. I'd not be super excited if I was wrong. But I think that the sort of creative novel, a novel math proof, the proofs we're seeing are really straightforward. The math problems the models are solving are very simple. And then they get tested on the Putnam the day after it comes out, which didn't leak into the training data, and they get 5%. So we have a ways to go. Can I
add to that in support of Luke, but more optimistic than Luke? so just run this thought experiment. We basically create papers out of deep research. You run deep research from any of these LLMs and create a bunch of papers. Then feed the deep research papers as input to further deep research, and they create deeper research papers, and keep going. What do you think will happen? Is that recursive self-improvement that is going to happen, or is it recursive self-impairment? It is going to be recursive self-impairment, because what is required in creating these papers is actual experiments and feedback from the world and hypothesis generation, all those things. It's not just combining and regurgitating stuff that is research, right? So that's in support of what Luke is saying, and I don't think Azalea is disagreeing here. But as a tool for AI scientists, I don't want to write boilerplate code. I want to have my parameter files to be automatically generated. I want to try a new idea if most of the code can be, and test cases can be automatically written. Yeah, that's definitely speeding me up. So that's, and a great efficiency boost, no matter what. Yeah.
So one more question there.
I have the mic, so
yeah.
I'm going to ask.
Yes.
Thank you for doing this. It's fascinating. My own interest is largely in what we might call visual intelligence, human visual intelligence. And I'm curious, at a high level, are the mechanisms by which an LLM functions the same as a visual diffusion model? Or are they different fundamental mechanisms, words versus images? And if they are different, is there something interesting in there of how we might use the multimodal to get to AGI?
I think Luke is working on this, right?
So there are differences that are fundamental. So language models that have primarily focused on language have a left to right constraint usually. So you go kind of one word at a time, left to right. And when you're picking a new word, you're really only looking at what's come before. It's really sort of a time series that way. And that has strong implications on the architecture and the kind of model you use. And then they also are what we call discrete. So in the end, they're picking from a set of options, which are the vocabulary or the words, right? The image generation models are fundamentally continuous, or at least pixels, as much as you have color resolution or whatever, they're very continuous, but they also don't have the left to right constraint. And so they typically start from noise or some sort of random full instantiation of the image, and then they can globally, everybody can look at everything, all the pixels, all the regions, and they kind of iterate and prove itself kind of in a more, sometimes it's called non-autoregressive, but not in a left to right manner. And so we've done a lot of research on hybrid models that can get the best of both worlds, and it's very open. It's not super clear how to do it, but the models behave very, very differently in practice.
Great. So can we get one here, please?
So I want to ask you on the continuation of this question. And let me call this a research parrots question, just for the sake. So we called LLMs stochastic parrots, but then ChatGPT happened, and everyone's using them because they're useful to language. And you said image models awful at binding, and as Luke said, generated trillion tokens, and they're still awful at binding in their activations, but they do 15 objects perfectly, and now there's 100 million people using them. Do you think research parrots will arrive? Like, if you write ML research papers, they have a verification mechanism because you write code, and you run the code, and you see what's the data efficiency of the model. That's not that hard. It's not deep, but if you generate 100 million random papers, one of them may pass, and are the ideas original? Maybe not even, but you can randomly sample strings. One of them will be original. Do you think research parrots will arrive before we as humans? Like, it's a little bit of a race, right? Will they be economical by a certain date? Will they outrun us as researchers?
Okay,
What's your thoughts?
Who wants to take that question?
I mean, you already know the answer of this panel to this question, given the previous questions.
So short answer.
I think, yes. Why not? I think the sample efficiency is going up in the models. They're becoming more and more interesting. They can solve more and more complex problems. So that's the way things are going. And then we throw in more compute for certain tasks. The value could be much higher than the compute that we throw in.
But will we have any role in this? Or will we just watch what they produce and read the one they select? And
I mean, they're already I don't know if you probably have in idea generation or kind of using as a co-pilot. I think it's already useful. Not all the time, but it has happened. There are cases that they're useful. So there are signs that they're useful, and this is this is a knob that's gonna kind of. I don't know the answer to whether probably human working with AI together is gonna be a super powerful combo, and this becomes more and more bold.
So my exact question is: do you think there'll be a time in the near future where the AI alone will be as useful as human with AI, which means the human will not add much?
Well, that's a harder question because
that's more like the AGI. They already gave their predictions.
Really.
But it's not AGI. It doesn't require robotics. It only requires code and math. It doesn't require the models to be like human brain. It doesn't require them to be data efficient. It still means we may lose our jobs.
That's probably going to happen. So sorry, let's go to that side of the room.
Can't rule out that at least in some domains, right? And this is also the Moravec's paradox, right? The most safe job might be things that have to do with physically, remodeling a house, pretty complex, and those jobs might be safer than some, if there is a job for just writing test cases, that might be much easier to automate. And some such domains might get automated. That I can't rule that out. I might not require AGI to get there.
I'll just very quickly say one more thing here, which is that if it's really novel research that you're aiming for, people have a hard time verifying correctness of that. So it really is going to be a superhuman behavior when it gets there, and that makes me more skeptical, but we'll see.
So I'm not sure how to properly phrase this question, but GPT 4.5 came out with 10 times more parameters than GPT-4, and the improvement wasn't as good as from GPT 3.5 or GPT-3. Right? So did we hit an exponential complexity wall with foundational models? Most of them improvements were in test time compute and data. Are we going to have more foundational models that are larger or different architecture, or we're just going to focus on the data and the test time compute?
I think my answer is a non-answer. I think that's $1 billion question for Frontier Labs, and I think I'm not sure if they know it, but I don't think we have concluded that
But do you have any kind of thoughts on the process? I'm sure you were like either surprised or not by the results of 4.5.
Do we know it's 10 times more? I don't think that number has...
I think there's a lot of unknowns, and I'll just do one of my rants about kind of open science here, which is that we don't have enough information to know what they really did, and no one should trust any result until it's replicated. So maybe OpenAI made a mistake in their setup. You know, they're not perfect. They have an amazing track record, but nobody's perfect, right? And so if you have like, I don't even know exactly how good it is. We don't even know how to measure that. They're getting so good, but we'll see. It's hard to know.
Oh, okay.
Thanks for the panel. So we've been talking about when we'll get to AGI and how. I have a question about when will we know and how will we know that we've gotten past the point of AGI? Because for context here, for 2 days ago, UC San Diego had a paper that GPT 4.5 actually passed the Turing test, so to say. And also, if we're looking at task completion or ability to perform on many of the things, I'm sure GPT-4 already outperforms 50% of the population on certain tasks today. What would that look like, the new Turing test?
Who wants to take that? Dilip has some ideas about when will I mean,
if the real AGI is passed, now I don't invent a new word, real AGI. So is achieved, then we will all know, because we'll be not working, playing, right? That's that's the whole idea there. That I want full automation so that we can all play. I think Arthur Clarke said this. So we would not be working, we'll be playing. That's when we will know that we have achieved a full AGI, and I don't know what's other definition.
That sounds very dystopian.
That merely makes me worry about super alignment, but that's a different discussion.
So I guess the answer is we really don't know how to measure. So
I think there's like sparks of AGI or something.
Oh my God, we're not going there. So yeah, here, please.
Thank you so much, everyone. Question more for Dilip. I would like to hear, what do you think is the role of neuroscience, cognitive science, psychology in the development of AGI, and more broadly to the other panelists, what is the future of interdisciplinary collaborations, and what are we missing that we're not just going to get through computer science?
Okay, neuroscience, cognitive science, all of them have a role to play if they are willing to question the dominant paradigm and throw probing questions out there for others to think about. But in some ways, it's challenging in neuroscience because experiments take longer to complete, and graduate students last only 5 years, and there are social pressures, so it's challenging because when there is a field that is moving so fast and improvements are month to month, and the remuneration scale is like 100x, it's very challenging for hard sciences to compete and give insights there. So I do think neuroscience can play a role in showing what is fundamentally missing, but it's really challenging. So I sympathize with the problem there.
We have time for one more question. So. Back there.
So relating a bit to a couple of the past questions, what do you think you'll be doing, like in your career and your job? Like, what will your life look like once we get to what you think AGI is? And then more broadly, like, what's the confidence you have that this will be good for the world? And what's like, what are the most important bottlenecks to ensuring that'll happen?
Okay, that's a lot of questions. Luke?
So for me, this is a little further off. This is not a super pressing issue, but it's a great question. And I'm not, I think there is a real risk that it will be bad for the world and, job displacement, I hope we're all just having fun, but that's not usually how job displacement works, right? And that's a real issue that's going to come sooner rather than later. And there are real practical risks well before AGI. Misinformation, bad data flooding everywhere, lack of trust in media. Like, there's real issues right now, and so those worry me a lot more than the long term. But they're both good conversations and good to think about. I don't know. I'm forgetting the other aspects of the question.
Yeah, I think it all depends on how we look at this AGI, but I think just like we right now we see this kind of phenomenon called vibe coding, like people can code who maybe didn't know how to code or didn't know much coding experience. Now they can code, maybe they can build a website, build an app and all that. I think this opens up new possibilities for humans, like maybe you can do research on how you do neuroscience and for how kind of bring insights from neuroscience to AI architecture. Maybe I don't have time to do that because I'm doing my own research and it needs some kind of more expert, acquiring this knowledge that I can just get much faster in that. So I think human creativity is going to remain and they're going to be more and more enabled to do more things as the AI becomes more and more powerful.
So I think maybe on that optimistic note, let's stop before we go into dark places. So thank you to our panelists, Dilip, Luke, Azelia. Thank you very much. It's been a pleasure. And Sampath, thank you for this event. And thank you all for coming.
Was it controversial enough?